Grade 12 Function, Section 3.6, Factoring Polynomials. So first of all, let's look at the remainder theorem and the factor theorem. So the remainder theorem is when a polynomial, f of x, is divided by x minus a, and the remainder has become equal to f of a. So if the remainder is 0, that means that x minus a is a factor of the polynomial, and this can be used to help factor polynomials. The factor theorem tells us that x minus a is a factor of f of x if and only if f at a is equal to 0. So you can see how the remainder theorem and factor theorem fit together, right? If we have our x minus a, if that gives us 0, that means then that that x value, that a value, will be a factor of your polynomial. Okay, so let's look at this more in depth. So here's an example that tells us to determine the remainder when our function, when this polynomial is divided by x plus 7. So the first thing we're going to do here is we're going to isolate the x value in this case. So we know that if we put minus 7 into our x plus 7 unit, that would give us 0. So we're going to actually take f of 7 in our given polynomial. And so f at negative 7 is equal to 0 times the quotient plus the remainder. So f at negative 7 is equal to minus 7 cubed plus 7 times negative 7 squared plus 2 times negative 7 minus 5, which gives you negative 19. So that's our remainder. So basically, the remainder theorem gives you a way, instead of having to solve the entire quotient, instead of having to divide the whole thing through, you can just input the a value. So this would be basically whatever value makes this entire term 0. So in this case, it would be negative 7. So you want to input that into your function, and once you do that, you'll get your remainder. So we can connect this to the graphical characteristics of the polynomial function. So in this case, they want us to sketch a graph of the function. So the first thing we can do here is we want to find a factor. So the way you can find the factor is you're going to test values. In this case, we got lucky. At 1 happened to be a factor. But basically, you're going to keep testing values, 1, 2, 0, negative 1, negative 2, etc., etc. You keep testing values until you get 0 equal to f of x. And once you get that, then you know that this, that x minus that value is a factor. So in this case, since I had f at 1, I know that x minus 1 is a factor. Let's say I had f of minus 1 in this case, then it would be x plus 1 as your factor. Okay, so then we're dividing it out using synthetic division in this case. And once you do that, then you want to factor the quotient. And then our function has zeros at 0, 1, negative half, and negative 2. So these are the zeros you can get. How do you find the zeros? We covered this previously. You just want to solve for x for each little part, each little term in your overall polynomial. So set 2x equal to 0, that will give you x equal to 0. In this case, x will equal to 1, negative half, and negative 2. Now once you do that, then you can sketch the graph. And we've discussed this previously as well, but the first thing you want to do, obviously, is put your zeros into the graph. Once you have the zeros, you want to look at the behavior around each point. So here we can see the behavior will be linear at each point. How do you know that? Because each term is linear. That comprises the polynomial. And then you can look at the overall degree. In this case, it's quartic, so you know it would look something like a W, which it does in this case. Perfect. The next way we can factor polynomials is using a grouping strategy. So you can actually group the like terms, or terms that are of similar degree, which is what they do in this case. And once you do that, you can then factor out an x, which is what they do here. So here we can see that in common they have x3 in common, so then x cubed times x minus 6 plus 2x times x minus 6, that's factored out. And then when you do that, now you see x minus 6 in common between both. So you can actually factor this entire thing out and bring it together, which is what you do here. And then they take these other two terms and factor them together, which is what they do here. And then once you do that, you can see you can factor the second term out even further. So then they do x, so they take the x out here, and they make it x times x squared plus 2. And then they bring this x here, this x minus 6 here, and the third term here. Okay. Perfect. So now we're going to look at some more examples. So we have this function here. And they're telling us that when, or this polynomial function right here, and it's telling us that when it's divided by x plus 1, the remainder is negative 12, and x minus 2 is a factor, so they want you to find m and n, because we don't have all the coefficients given to us yet. So they give you enough information here to actually find the values of m and n. So the first thing you can do is, because you know that once it's divided by x plus 1 and the remainder is negative 12, you can set up an equation that gives you that, right? So what they do here is they say that f at negative 1 is equal to negative 12. How do they get the negative 1? The negative 1 is given right here. They know that the value of x that would give you a 0 for this term is negative 1, so they put that negative 1 into the function, and that would be negative 12. So then they solve for the function. So they put in this negative 1 into this function right here, and once they do that, they get this final equation. So this isn't the end yet, but you see they label it as equation 1, so that's really important. So we have our equation 1 that we found, which is really important. And the second thing they can use is the fact that x minus 2 is a factor. So since x minus 2 is a factor, that means the remainder is 0, right? So f at 2 is equal to 0. So then again, they follow the same process. They take f at 2, they set it equal to 0, and then now we have the same process right here. And then now they're just using systems of equations. So you should have covered this in like grade 10, I think. But now you're just substituting the pieces in. So here they're substituting in, they're isolating for m in this case, and they substitute that m from equation 1 into equation 2. And then once they do that, now everything's in terms of n, so they can solve for n. And then once they solve for n, they're putting that n back into equation 1 in this case, and they're solving for the m. So now they have the pieces n is equal to 3, m is equal to 5, and now that you have that, you can put it back into your original polynomial function, and you get your overall polynomial being this. Perfect. So in summary, there's a couple of key ideas. You want to know, we covered so far the remainder theorem and the factor theorem. So the remainder theorem tells us that when a polynomial is divided by x minus a, the remainder is equal to f at a. And the factor theorem tells you that x minus a is a factor of f at x only if and only if f at a is equal to 0. So a couple things you need to know. To factor a polynomial f of x of degree 3 or greater, you can use a factor theorem to determine a factor of f of x. So the way you do this is you just want to keep testing values, and you keep testing them until you get f at x equal to 0. And once you get that, then you know that that value gives you a factor. Then you want to divide the function by that factor, and then factor that quotient you get even further if possible. And so if the polynomial is a degree greater than 3, it might be necessary to use the factor theorem more than once, right? Because if you think about it, if you had a degree greater than 3, that means that your resulting quotient would be really, really big, right? And it might be, degree 4, degree 5, whatever it might be for that quotient itself. And so you might need to apply the factor theorem again for that. And then not all polynomial theorems are factorable. Okay, so now we have a lot of examples. So the first one being, given this function, determine the remainder when f of x is divided by each of the following binomials of the dividing. So now that you've learned the remainder theorem, this is really easy. All you need to do, for example, you want to put in f at 2, because you have f at x, is equal to x minus 2 times the quotient plus the remainder. So then put in x at 2, x equal to 2, then you'd get your remainder, which is what we do right here. So I put the x value, I put x equal to 2 in this case, and now I know my remainder is 64. So I followed the exact same process for the other two examples. And then the third question asks you, are any of the binomials in part A factors of f of x? And the answer is no. How do we know that? Because we don't have any zeros, right? If we had 0, let's say I had any of these equal to 0, then I would know it's a factor. But since in this case they all equal to numbers that are not 0, I know it's not a factor. So here we have again, x minus a is a factor of f of x if and only if f at a is equal to 0. So then which of the following functions is divisible by x minus 1? Okay, so what you want to do here is you want to sub in x is equal to 1 into each. We're using our factor theorem here. So you want to sub that value in, and we want to check our final values, right? So in this case, we can see that these two values, they're giving us an f at 1 that is equal to 0, and 1 that is equal to 0. So that's how we know that these are factors. But for these two, they're not. So these aren't factors. Okay, factor fully. So here, this is what I was talking about previously, where sometimes they'll give you a question where they're giving you just the polynomial function, and they're not telling you what you need to factor by. So in order to do this, you can still solve this, but all you need to do first is find a factor. So you're going to use a factor theorem, and you're going to test values. So in this case, I tested 1, I tested 2, and once I tested 2, I got a factor. So I know that x minus 2 is a factor. And then once I do that, I'm going to use the process of polynomial division. So the first thing I want to do is get rid of the x cubed term. So I know that if I multiply this entire thing by x squared, then I'll get x cubed minus 2x squared, and that will get rid of my x cubes. Perfect. And then I want to then get rid of the 11x squared that is found here. So if I multiply this term again by 11x squared, by 11, just 11x, then I will get my 11x squared, and that will give me 11x squared minus 22x. Perfect. So that gets rid of these two. I'm doing something! Then the next step is to get rid of the 30x minus 60, and we got lucky here actually because this is a perfect, this divides it perfectly out. So if I multiply this by 30, then I get the 30x minus 60 required, and then my overall thing is 0. So by the 0 at the end, I then know that this is a perfect factor and that there's no remainder at the end. Okay, and so now that we've set up this function here, we have our main term, we have the quotient, and we can actually divide this even further, factor this even further, giving us the resulting function. Factored out. Perfect. So in this section, we learn more about polynomial factoring. We looked at some examples. Try and get familiar with the factor theorem and the remainder theorem. Those are really important. It'll make your life a lot easier when you're factoring, and you can find answers you need a lot faster. So with that, thank you for watching. If you have any questions, feel free to contact us on our website, www.passionateminds.com.